Morning, everyone. My name is Liu from Mechanical Engineering Department of Polytechnico di Milano. The title of my project is A Branch and Bound Approach for the Stochastic to-Machine Flow Shop Scheduling with Rework. Firstly, I will introduce the motivation of this project. Refurbished products are gaining importance in industrial sectors, specifically for the high-value products, to guarantee the economic cost and the sustainability. Gas turbine is the most efficient way to generate power, and the turbine blades are one of the most important parts inside the gas turbine. The turbine blades are really expensive. A single blade equals to the middle-range car, and the life cycle of a gas turbine is about 25,000 hours. After this, the blades need to be disassembled and maintained. Due to the high value, the customers often require the refurbished blades. So we say that the turbine blades match the typical characteristic of remanufacturing and the circular economy business model. The remanufacturing process of turbine blades is really complicated. The blades are processed in batches. Firstly, the blades are disassembled and shipped to the manufacturer, and then the blades are inspected to assess the damage level. The unrepairable blades are discarded. Only for the repairable blades, the repair process starts. And there are several key activities inside the repair process. Firstly, remove the damaged parts of the blades by defect removal operation, and then restore the removed material through laser welding technologies, followed by a grinding process to machine the blades to the desired shape. And finally, the non-destructive test to verify complete removal or defects. And then after the repairing process, the blades are reassembled and shipped back to the power plants. As I have mentioned, this process is complicated, but in this work, we just focus on our attention on the subset of two operations of the repairing process: the laser welding and the following grinding process. These are the two bottleneck resources of the whole repair process. And a rework is needed for all the blades in a batch. Thus, the same process is repeated twice on the same resources, as described in this figure. The repair process is affected by a significant degree of uncertainty. Firstly, blades entering the process with different wear states, which means the repairing time could be different for each blade. So the processing time is uncertain. And secondly, the blades with severe defects could not be repaired. This means some blades in the batch are discarded and replaced with new ones. This will lead to the uncertain number of blades in a repair batch. Grounding on these 2 points, the processing time of each batch is uncertain. To hedge against the uncertainties, robust scheduling approach is needed. In this project, we use the risk measure approach. Risk measure can estimate the stochastic feature and is less conservative than the min-max regret approach. It stems from the financial optimization area and popular in the scheduling field nowadays. Specifically, we use value at risk. To use it, firstly, we describe the uncertainties associated to the processing times, and then derive the distribution of objective function, and finally evaluate the value of VAR. With it, we can say the maximum objective function we can experience in the best alpha percentage of scenarios, or we can say the alpha level, we have the alpha level confidence that the objective function will not excess the VAR value. Okay, now I'll summarize the problem statement. batches of blades have to undergo a two-stage process. This is the two-machine flow shop scheduling problem, and the processing time is uncertain. All the batches need to be reworked by repeating the same sequence of operations. Mix by is taken as the object function since this repair process wants to maximize the utilization of the considered resources. Value at risk is used. Approach is used to mitigate the impact of uncertainty. Then I'll introduce the structure of the problem and how hard is it. The activity network can be represented by a set of operations with the precedence relations and the stochastic durations. The uncertain processing times is needed to be described by general distribution to match the characteristic of the industrial problem. Grounding on this, we want to calculate the value at risk by estimating the distribution of the mixture. And then we want to find the optimal schedule, minimizing the value at risk among all the scheduling decisions. This is an NP-hard problem. Then I'll introduce how we solve this problem. For the activity network, we use Markov activity network to represent all the operations and precedence relations. Phase type distribution is used to approximate the general distributions. And it can be incorporated in the Markov activity network. Grounding on this, on top of this, we can calculate a continuous time Markov chain is built and to derive the distribution of mixture. And the bisection method is used to calculate the value at risk. Then we develop a branch and bound algorithm to find the optimal schedule, minimizing the value at risk. Before going to the branch and bound algorithm, I'll introduce how we deal with the rework. The rework activities are modeled as additional jobs. We use the activity on arc network to represent this project. The dashed lines denotes the precedence relations, and the prime A1 prime A2 prime denotes the rework of job. The rework job should be scheduled after the processing of the job for sure. And also in the real environment, an offline inspection step is operated before the rework. So we said that the rework jobs cannot be processed earlier than 2 jobs after the corresponding original job. Then we move to the branch and bound algorithm. This is the classical algorithm to solve scheduling problem. Branching scheme for schedule and partial schedule evaluation and initial solution schedule are presented in this work. We use the simplest branching scheme, sequence the jobs starting from the beginning of the schedule. Then I'll introduce the for schedule of the leaf nodes evaluation. Suppose we have this for schedule with all 8 jobs are sequenced, and then we can have this activity on arc network as I have introduced with all the precedence relations. Then we develop an automatic continuous time Markov chain generation scheme. Basically, we generate all the possible states in this project from the beginning of activity A1 to the end of activity D2 prime. But we blocked it, so this generation scheme is automatic. With this continuous time Markov chain, we can get the infinitesimal generator matrix with the advantage of the chronic operations. This is referring from another literature. Once we have this generator matrix, the CDF or mixed span distribution can be calculated by this distribution. And then value at risk can be calculated by exploiting the bisection method. Note that to reduce the iteration steps in the bisection method, for the activity node A, we set the lower bound support of the bisection is the VR value of its parent node, and the upload support is set as the current basis solution. If the root cannot be found in this support interval, this node can be pruned. This can reduce the iteration steps and speed up the algorithm. In order to evaluate the non-leaf nodes, we must be able to evaluate the partial schedules. Suppose we have this partial schedule with 4 jobs scheduled and another 4 jobs unscheduled. Firstly, we did convolution operation for the 4 unscheduled jobs to take them as one single job X. Here we relax the precedence relations between the 4 jobs. And then we built this activity on arc network for the new schedule. And then we relax the precedence relation between the X1 and X2. Okay. Value at risk or mixed span is a regular objective function, so this provides a lower bound. Then the continuous time Markov chain generation scheme for leaf nodes can be used to estimate the lower bound of value at risk. The lower bound will guide the search and cut the branches without a possibility finding optimal schedule. This is the basic idea of the lower bound development. To set the initial upper bound for the branching tree, an initial solution schedule is generated. This schedule is obtained by arranging all the jobs according to the decreasing order of EG1 minus EG2. EG1 and EG2 are the expected value over the processing times of job J on machine 1 and machine 2. Actually, this is the optimal schedule for 2-machine flow shop scheduling problem with exponential distribution time. If the resulting schedule is in conflict with the constraints between the rework jobs, they are shifted towards right until the conflicts are eliminated. The result schedule will be set as the initial solution schedule, and the VR value will be the initial upper bound of the algorithm. Okay, that's all about the branch and bound algorithm. Then I introduce the implementation of this algorithm. The phase type distributions are modeled using Build Tools library. This is the rich toolbox for Markov performance evaluation. The branch and bound algorithm is implemented with the support of the Bob++ library. This is the framework for solving optimization problem with branch and X methods. Matrix-related operations are performed by means of the agent library in C++. And the experiments are run on the workstation. The proposed algorithm is tested on randomly generated instances. The number of jobs is 6, which means 12 jobs in total, including the rework jobs. The processing time of each job on each machine follows the general phase type distribution, with the mean value and the number of phases randomly generated. 10 and 20% of risk level are used, and 50 instances in total are generated for the experiments. Then I'll introduce the algorithm performance. We use the experiments to assess the performance for the proposed approach in terms of solution time and the number of nodes explored. The proposed algorithm is able to find the optimal schedule in about 15 minutes on average, from 2 to 13 minutes. And about 10,000 nodes are evaluated for each instance in the branching tree. The average evaluation time for single node is about 0.08 seconds. We found that the node evaluation time entails the largest part of the solution time. So we studied deep into it and found that as a clear positive correlation between the single node evaluation time and the maximum and the matrix dimension. Also, we investigate the efficiency of the initial solution schedule and the lower bound. The initial solution provides a good schedule. The optimal solution is updated less than 20 times, and the leaf nodes evaluated count less than 3% of all evaluated nodes, proving the efficiency of the lower bound. Furthermore, we analyze the performance and the different risk levels. ANOVA tests are performed, but we didn't find any statistical evidence to state that the solution time is affected by the risk level. Okay, that's all about the algorithm performance. Now I will conclude this presentation. We studied the scheduling of manufacturing activities for the repair of turbine blades. This problem can be defined as a two-machine flow shop scheduling problem with uncertain processing time and rework. The objective function is minimization of value-at-risk of mixed span. Phase-type distribution is used to fit the uncertain processing times, and Markov activity network is exploited to evaluate the distribution of mixed span. A branch and bound algorithm is developed to find the optimal schedule. But we have to say that the computation time to solve larger instances is rather high. So we are still working on this to speed up the node evaluation and develop tighter lower bounds. Also, the current rework is deterministic. Probability of rework may be considered in the future research. Okay, that's all about my presentation. Thank you very much for your attention, and I'm happy to answer any questions.